Let us see here the NMR spectra of ethanol. The structure of ethanol is shown here. The high resolution NMR spectrum of pure ethanol is given here. The methyl protons couples with the methylene proton to give triplet n plus 1. By following the n plus 1 rule, it gives triplet. Similarly, methylene proton couples first with the methyl protons to give tetrate, and it further splits into doublet due to coupling interaction with the OH proton. And the OH proton on coupling with the methylene protons to give triplet n plus 1, 2 plus 1 triplet signal. Whereas in the presence of acid, when you add acid to ethanol, the proton, the OH proton undergoes continuous exchange with the acid proton. As a result, it becomes a singlet. And the methylene protons do not couple with the OH proton. Here we will study about nuclear double resonance NMR technique. In double resonance NMR technique, it uses two different radio frequency pulses called double irradiation or spin decoupling technique. It is very useful and advanced NMR technique for simplification and interpretation of complex NMR spectra of complicated molecules, protein molecules, etc. For example, in this I have shown the NMR spectrum of pure ethanol. When methyl proton is irradiated, it collapses and the signal disappears, and also CH3 proton does not couple with the methylene protons. Therefore, methylene proton couples only with the OH proton to give doublet. In this, we will study about what is nuclear Overhauser effect, what is NOE. For example, this is a protein molecule or organic molecule where there are three protons, A, B, C. So there are three different protons, they give three different chemical shift, and A and B are spatially closer together, whereas C is not closer together. When using double resonance technique, when A proton is irradiated, there is a change in the intensity of the NMR peak of the B because A and B are close to each other. The signal increases. If the signal increases, amplitude increases, it is called positive nuclear Overhauser effect. If the signal of the B proton decreases, then it is called negative nuclear Overhauser effect. In other words, there is a change in the intensity of the nucleus B when the nuclear spin states is perturbed. This phenomenon is known as nuclear Overhauser effect. This effect is very important because NOC spectroscopy, 2D NMR spectroscopy are based on nuclear Overhauser effect. And it is very useful for the three-dimensional structure determination of organic compounds, including proteins, the DNA, etc. For this effect, Overhauser was awarded Nobel Prize. NOE effect occurs through space as due to dipole-dipole interaction relaxation. Its magnitude is inversely proportional to the sixth power of the distance between the two interacting nuclei. for example A and B in this case, it is useful for the studying the three-dimensional structure and stereochemistry of organic compounds. Here, let us study the effect of chirality on NMR. Most of the amino acids are chiral molecules. They have asymmetric carbon atom in it. For instance, cysteine is an amino acid. If you look at the 2D structure, the methylene protons are equivalent or identical or expected to be equivalent. The methylene carbon atom is pro-chiral. If you look at the 3D structure, the methylene protons are not chemically identical. They are chemically distinct and therefore resonate at different chemical ship values, as you see here. And for example, Hp proton couples with the Hc proton because they are not chemically equivalent. They are also not magnetically equivalent. And further, it couples with the A proton to give tetrate. We will further study dynamic NMR, temperature dependent NMR, NMR of fractional molecules. In the case of ethane, there are two methyl groups. The two methyl protons, 6 methyl protons are equivalent because of CC single bond rotation. They are very fast on NMR time scale compared to NMR time scale. Therefore, it appears as a singlet. In this, we will study the conformational exchange process in cyclohexane molecule. There are two types of protons in cyclohexane: axial proton, equatorial protons. Due to ring flipping process, axial proton become equatorial and equatorial proton becomes axial. Therefore, at room temperature, two signals are expected due to axial and equatorial protons, but at room temperature, only one singlet signal is observed, single average resonance is observed, whereas on lowering the temperature, for example, at high temperature, a single average resonance is observed due to fast exchange in flipping process. The interconversion of axial to equatorial, equatorial to axial due to spin flipping is so fast. On decreasing the temperature, the two signals are resolved now. In this, let us see the effect of temperature and magnetic field on the NMR spectra of fractional molecules. With the increasing temperature, there is a fast exchange and the two signals slowly merge and become single sharp line. With the increasing field strength, the two signals are well resolved. Here, how NMR is used to study hindered rotation in N prime dimethyl formamide. In N dimethyl formamide, there are two methyl groups. These two are at low temperature. The two protons are chemically distinct. Therefore, they will give two signals, as it is shown here. As you increase the temperature, the two signals just merge at that time. Tau equal to the residence lifetime, the lifetime of methyl proton A in this state, square root of 2 pi nu A minus nu B, where nu A and nu B are the resonance frequencies of the two methyl protons. Using the temperature dependent NMR, we can calculate the rotational rate constant for this hindered rotation process. We know that 1 by tau lifetime is equal to the rate constant. Therefore, the rate constant for this rotational exchange process can be calculated using dynamic NMR. Here, we will study what are fluxional NMR fluxional molecules. These fluxional molecules are molecules that undergo dynamics, constantly exchanging their positions. For example, PF5, SF4, these are all trigonal bipyramidal geometries. They have trigonal bipyramidal geometries. They undergo very pseudo rotation. That is, it occurs via square pyramidal geometry. The axial, due to this rotation, axial positions become equatorial, equatorial becomes axial, as you see here. The DPP and square pyramidal geometries, the energy differences are very little, therefore they undergo very pseudo rotation to give functionality, functional character. For example, PF5 fluorine 19 NMR is used to study the pseudo rotation. In this case, carbon 13 NMR is used to study the functional character of this molecule. Fluorine 19 NMR is again used to here. The structure of SF4 is obtained from the NMR. For example, at room temperature, single peak is observed. For example, because of constant exchange of axial and equatorial position, they are equivalent. They are equivalent. All the fluorine atoms are equal. On lowering the temperature, it splits into two signals. First, it splits into two signals due to axial fluorine and equatorial fluorine are chemically distinct. Further, on lowering temperature, each peak is split into triplet. For example, the axial fluorine are split into triplet because of this coupling with these equatorial two fluorine atoms. Each peak is split into triplet. Let's see quickly a few applications of NMR to inorganic molecules or inorganic compounds. One, metal hydrogen bonding in this complex molecule is established using proton NMR. The nuclear quantum number of rhodium nucleus is 1 by 2. Therefore, proton NMR gives a doublet because of the direct bond coupling gives a doublet. This establishes a bond between rhodium and hydrogen. The structure of phosphorus acid is elucidated by using phosphorus NMR. The formula of phosphorus acid is H3PO3. There are two possible structures I have given here. In this case, phosphorus 15, I'm sorry, this is phosphorus 15, I equal to 1 by 2. And the phosphorus NMR, using phosphorus NMR, this compound will give you a doublet, whereas this compound will give you a triplet. The OH protons does not couple because of fast exchange with the water molecules in the solvent. In actually, triplet signal is obtained. Therefore, the correct structure is this one. Similarly, the structure of fluoroderivative is also obtained. What is the structure of PF6 minus? It is elucidated using phosphorus 31 NMR. Sorry, previously I told 15 phosphorus 31 NMR mass number. It gives a septed signal, 7 lines. It reveals that that is fluorine phosphorus NMR. There are 6 fluorine atoms. Therefore, phosphorus couples with the 6 fluorine atoms to give septed signal, 7 lines. It reveals that all the fluorine equivalent. Therefore, the geometry is regular octahedral. pH 4 plus, like NH4 plus, ammonium ion, phosphonium ion. Using phosphorus 31 NMR, it gives a phosphorus 31 couples with the 4 proton to give quintet 5 lines, n plus 1 with intensity ratio. Whereas proton NMR, all the protons are equivalent. It couples with the phosphorus 1, I equal to 1 by 2. Similarly, BRF5, the structure is studied by using fluorine 19 NMR. In this case, there are 2 peaks were observed with intensity ratio 4:1. It shows that there are 2 kinds of fluorine. 4 are one type and 1 is a different type. The intense line is doublet. The intense line is because it then 4 equatorial, 4 real fluorine atoms couple with this proton to give 10 signal. Because of 4 fluorine atoms is doublet. Weak line, this is only 1 fluorine atom couples with the 4 painted 5 lines. Therefore, the structure is symmetrical tetragonal pyramid from NMR studies. NMR is also used to investigate the cis-trans isomers. For example, in platinum complex, the cis isomer will have different coupling. Platinum I equal to 1 by 2, phosphorus I equal to 1 by 2, coupling constant, it is cis 3.62. From the coupling constant values, the cis-trans isomers can be determined. In fluorine 19 NMR, the structure of dimethyl phosphorus trifluoride structure is elucidated. At low temperature, 2 peaks are observed. At room temperature, due to perirotation, fast exchange, only 1 peak is observed. That are all are equivalent. 1 fluorine in axial position and 2 in equatorial position. Using NMR, this structure is up. Here we will study what is magic angle spinning. Only it is important in solid state NMR. In solid state, the compound gives broad line in NMR spectrum because of increased line width due to spin lattice relaxation, to fast spin lattice relaxation, to dipolar chemical shift anisotropy. These effects are averaged out in solution. When the compound is dissolved in solution, these effects are negligible. These effects NMR spectrum due to rapid tumbling motion. However, in solid state, these effects are very significant. The sample is rotated about this axis, makes an angle with the external applied magnetic field, theta equal to 54.74 degree. The dipolar chemical shift anisotropy is directly proportional to 1 minus 3 cos square theta. When theta equal to 54.74, these two effects become zero. Therefore, the lines are narrowed with the lower line width or line. It is well resolved at this magic angle spinning of the sample. We'll quickly see the EPR spectroscopy. In the absence of magnetic field, the two spin states are degenerate in the presence of external applied field. The two states splits. The energy of separation is given by, we have seen earlier, G, E, beta, E naught. That beta is the Bohr magneton. E is the value. E naught is the applied field strength. H nu, the resonance condition is H nu equal to Ge beta E naught. The electron spins about its own axis and also rotates, revolves in an orbit. As a result of this, there will be, I forgot to tell, ESR spectroscopy is also called electron spin resonance spectroscopy or electron paramagnetic spectroscopy, resonance spectroscopy, or electromagnetic resonance EMR spectroscopy. How the EPR spectra are presented? Because of this transition between the two electron spin states, there will be an absorption signal. The absorption signal, as you see, it is not well resolved. There are so many peaks. It is buried. So the derivative signal in EPR, the signal is always presented in first derivative. When you take the first derivative of this absorption signal, the hyperfine splitting signals are well resolved. Here, absorption and derivative EPR spectra. Why derivative EPR spectra are important? EPR is a very sensitive technique than NMR. However, due to short relaxation time, we have seen earlier, as in paramagnetic system, the absorption signals are always broad, and hyperfine structures, we have seen earlier in the slide, hyperfine structures are buried. Therefore, derivative signals are obtained using phase sensitive detection technique. Get well resolved hyperfine. Here I have shown the schematic diagram of EPR spectrometer. It consists of electromagnet similar to NMR, sample holder, and amplifier and detector. In this case, we will use microwave bridge. It is used to generate the microwave, monochromatic microwave. For expand, it is 9.8 gigahertz. For expand, it is 9.8 gigahertz. It will produce one diode. Is used to generate the monochromatic microwave radiation. It uses phase sensitive detector to convert the absorption signal into derivative signal. It is the actual EPR spectrometer. These are electromagnets. This is a microwave bridge, microwave guide, and you have temperature controller, liquid helium to measure low temperature EPR. Similar to spin-spin coupling constant in NMR, in ESR we have hyperfine coupling interaction, hyperfine splitting. It is represented by A, whereas in NMR it is represented by T. It occurs due to the coupling between the spin magnetic moment and the nuclear magnetic moment. We will see further. The spin Hamiltonian for the EPR is H cap equal to H cap E electron Zeeman plus hyperfine coupling interaction. Hamiltonian corresponding to the energy of this Hamiltonian is given by this. We have studied this in G mu B B ms, where ms is the number plus or minus half, and hyperfine coupling term. A is the hyperfine constant. Ms is the magnetic spin magnetic quantum number. Nuclear magnetic quantum number Mi. For liquids and gaseous samples, the hyperfine coupling interaction are isotropic because of constant tumbling motion. Anisotropic effects are averaged out as we see in magic angle spinning, For solids, there will be anisotropic. The hyperfine coupling is anisotropic. At different angle measure will give different value because of anisotropic factor. ESR signal further splits into several lines because of this hyperfine splitting as in spin-spin coupling. What are the important characteristics of hyperfine coupling? As the spin-spin coupling, it is similar to spin-spin coupling. It depends on the magnitude of nuclear and electron spin magnetic moments. Electron spin density near the nucleus, because electron spin couples with the nucleus, called a thermic contact term. Similar to J value, A value is independent of applied magnetic field. And n plus 1, it obeys equal to 1, then 2ni plus 1 is similar to spin-spin coupling. The intensity ratio is given by Pascal triangle. In NMR, chemical shift value, similar to chemical shift value in ESR, G value is obtained. Ionic free radicals, the spin by 2 is the lowest energy state, whereas in the case of NMR, plus 1 by 2 is the ground state. Therefore, by following the selection rule, delta Mi equal to plus or minus 1, therefore, there are two signals. There are two signals obtained due to hyperfine splitting due to I equal to 1 by 2. The hyperfine splitting constant is calculated from the spectra as shown here. Let us see few more examples. Cylopentadienyl. Here it is a free radical. It's a paramagnetic molecule. The electron is delocalized. The unpaired electron is delocalized over 5 stud. There are 6 lines observed. In the case of benzene radical, the unpaired electron density is delocalized over 6 hydrogen atoms. Therefore, there are n plus 1 septet. There are 7 lines observed with the intensity ratio using Pascal diagram. It is obtained 1, 2, 3. Let us now see naphthalene anion radicals similar to benzene anion radical. Here there are two types of protons: alpha proton, 4 alpha protons and 4 beta protons. Therefore, they have different chemical shift as well as different coupling constant. For example, the coupling constant alpha alpha proton is 4.9 Gauss, A beta is 1.83 Gauss. The unit for hyperfine coupling J in Hertz. The formula used to calculate the number of lines is 2ni plus 1 into 2ni2 plus 1. Therefore, 2 into n4 and proton I equal to 1 by 2. Therefore, there are 25 lines. It agrees with the number of lines obtained in the actual NMR spectra. Here, what is McConnell's relation? This gives the relationship between the hyperfine coupling constant and the unpaired spin electron density. If the unpaired electron spin density is larger, then the hyperfine coupling constant is larger. The unpaired electron couples with the proton. A is equal to Q rho C, where Q is a personality constant. It is 230 Gauss. Using this expression, once you know the hyperfine coupling constant from the experiment, Q value is known, you can calculate the unpaired electron density. Rho C will give the unpaired electron density distribution. Using the chemical reactivity site. Here we will study the EPR of DPPH radical. It is an EPR reference compound similar to TMS. Tetramethyl silane is the phenyl picryl hydroxyl radical, is a reference for EPR. It is a field marker. It is a field marker. For example, this is the EPR spectra of in the solid state. It occurs as it exhibits a single line because of exchange narrowing due to Heisenberg spin exchange. DPPH in the solid state gives a single line due to exchange coupling, exchange narrowing. Okay, let us see the structure of DPPH. The unpaired electron is delocalized over two nitrogen atoms. Therefore, there are two nitrogen atoms, 2Ni plus 1. There are two as up here. It is very, very important. Was asked in CSIR or gate. DPH is a field marker. Using this, the G value for the since the G value for the DPPH is 2.0023, it is known. Therefore, the G value for the copper complex, iron complex, or any free radicals is calculated using this as reference compound. EPR of methyl radical. In this case, the unpaired electron is coupled with the three protons. In the presence of magnetic field, the electron spin state splits into two. It further couples with one proton to give doublet, and similarly it couples with the other three protons. There are four transitions based on the selection rule delta mi equal to plus or minus 1. We can calculate the number of lines, the energy levels of using this formula. EPR of nitroxide radical. These nitroxides are very important organic radical compound used in spin labeling, ESR spin labeling. We'll see further. The unpaired electron is in the nitrogen atom, the oxygen atom, delocalized over this bond. Since hydrogen is NMR active, oxygen is not, oxygen 16 is not NMR active. We have seen earlier, In equal to 1, S equal to 1 by 2. Therefore, there are three lines. They are of equal intensity. It splits into triplet. E equal to 1, minus 1, 0. The hyperfine coupling constant is given as is calculated follows. Similarly, EPR spectra of para-benzoquinone radical anion. The structure is shown here. The unpaired electron is delocalized tons. So n equal to 4, n plus 1. 5 lines are obtained with the intensity ratio. We'll quickly see NMR and EPR problems. NMR and EPR problem asked in CSIR gate exams, gate jam. Using the resonance condition, ESR resonance condition, NMR resonance condition, Larmor frequency, pulse angle. Several problems were asked in GATE, CSIR and IIT JAM. For example, we'll solve here a few problems. Calculate the proton NMR frequency in magnetic field of 1.5 Tesla Gn, nuclear G value, and nuclear magneton is given. You know the proton resonance frequency is as h nu. We know that according to resonance condition, nu equal to Gn, beta n or mu n v. On computing n, mu n or beta n, we'll get the proton NMR frequency 63.8. In this problem, they have asked to calculate the magnetic field. In this equation, if you know nu, you can calculate B. If you know B, then you can calculate nu. In this case, they have asked to calculate the magnetic field required for proton magnetic resonance. Nu is given. They have asked for B, similar to previous problem. In this problem, Based on Larmor frequency, they have asked this problem. Calculate my gyromagnetic ratio of fluorine 90 nucleus with the NMR frequency in a magnetic field 1 Tesla. According to Larmor frequency, you know Larmor frequency is directly proportional to the applied field strength equal to gamma proportionality constant. Therefore, gamma equal to omega by d. You know omega equal to 2 pi nu. We have studied previously. On substituting, we will get this answer. Similar to EPR problems, in competitive exams, they ask using the resonance condition, G value, etc. Calculate the G value of the unpaired electron placed in magnetic field 0.33 Tesla at resonance frequency 9 gigahertz. So you are asked to calculate the G value. Therefore, you are given the frequency, resonance frequency 9.0 gigahertz is 10 power 9 per second. Hertz is per second. 9. On substituting, we'll get the G value 1.9895. In this problem, they are asked to calculate the ESR resonance frequency. They have given the magnetic field. They have asked the ESR resonance frequency. Substituting, you will get this result. In my research in Medical College of Wisconsin, we have studied on cancer. So we have taken the cancer tissue and put into the EPR tube and measured the low temperature EPR. The EPR spectrum for cancer tissue is shown here. The spectrum is obtained is similar to transferrin EPR, protein EPR. Transferrin is a protein is overexpressed in cancer tissue as cancer cells require more oxygen for its growth. Using EPR spectroscopy, it is reported that it is used to study the spin crossover phenomenon. It is used to study the spin crossover phenomenon in iron 3 complex. For example, heme. It is present in the active site of several proteins, cytochrome C, myoglobin, hemoglobin, cytochrome C oxidase, etc. This is the high spin ion complex. The G value, this peak, the black one corresponds to high spin. On adding ligand, imidazole, for example, converted into low spin complex. High spin complex is converted to low spin complex. The low spin complex is formed because of it decreases. The spin conversion can be studied using an ESR, EPR spectrum. Free radicals are produced in our body in large excess when you suffer from ischemia, heart attack, or any cardiac diseases, neurodegenerative diseases. They cannot be studied by directly by using ESR. So nitrones, TMPO, or simple organic compounds, they react with the hydrogen. Can be studied by EPR. Are trapped by the different free radicals are trapped by gives a characteristic EPR spectrum. For hydroxyl radical, you will get this characteristic spectrum. From the EPR spectrum, we can determine the free radicals formed. Mixture of free radicals formed, we can do spectral simulation. I have shown how the spectra is simulated, how the ESR spectra is simulated. Using spectral simulation, we are able to suppose a mixture of free radicals formed. Using simulation, we can determine from experimental spectra. How ESR dynamic therapy. For example, photodynamic therapy is used for cancer cure. In this photodynamic therapy, photosensitized drug in the presence of light, it is excited and it transfers its energy. It transfers its energy to triplet oxygen to give singlet oxygen, which is highly energetic. Or or the excited photosensitizer can transfer an electron to triplet oxygen to form superoxide radical, or it can generate hydroxyl radical. There are two types of mechanism: type 1 mechanism, formation of free radicals, and the formation of singlet oxygen. Using ESR spectroscopy, the mechanism of photodynamic therapy can be obtained. Similarly, free radical intermediates can be detected ESR spectroscopy. ESR spin labeling is an important tool to study the dynamics of DNA, RNA, protein molecules. For example, nitroxides on reaction with the SH group, it forms a compound. Now the protein is spin labeled. Therefore, we can follow the using site-directed mutagenesis. We can attach the nitroxide spin, and we can study the distance between the two spins used by measuring this spin relaxation time we have studied. We have in Medical College of Wisconsin, we have developed they have developed saturation recovery instrument to calculate the spin relaxation time. Using that, they will study the spin labeling and the protein structure. Using the ESR spectra of the nitroxide radicals sampling from the line width, from the line shape, we are able to study the dynamics of proteins or small molecules. The EPR spectra of different copper complexes. For example, A is the oxidase activity. Thiol oxidase activity of SOD1 was studied by our group using spin trapping method, as well as ESR, Endor, electron nuclear double resonance spectroscopy, and NOSI NMR spectra. We have also used advanced EPR techniques to study the active site changes, active site geometry changes in SOD1 during thiol oxidase activity and peroxidase activity using 3-pulse eSIM electron spin echo modulation spectra, 4-pulse high score spectra shown here. We have used electron nuclear double resonance spectroscopy ENDOR and EPR to directly probe the copper active site and free radical formed during the bicarbonate dependent peroxidase activity and published in Journal of Biological Chemistry. Using low temperature EPR, we have identified the tyrosyl radical formation when bovine SOD1 superoxide dismutase, superoxide dismutase, is exposed to UV light. Tyrosyl radical is produced. Using simulation, the parameters are obtained. And in the case of wild type human SOD, a tryptophan radical is obtained. Using simulation, we have identified this as a tryptophan radical. We have also produced mutant. Tryptophan is replaced by phenylalanine, phenylalanine. In that case, no tryptophan radical is obtained. It is obvious. We have replaced the tryptophan by phenylalanine. Therefore, there is no tryptophan radical is formed on exposure to UV light. So, ESR spectroscopy is very much used in studying the free radicals, protein dynamics, and has got a lot of applications. I have received more than 1 crore funds from various funding agencies. SERB, DST recently I have received, and the Department of Biotechnology, New Delhi. I have received grants 2 times from Department of Biotechnology, and the DRDO, New Delhi, DRDO, DIPAS, New Delhi, and UGC. Without my PhD boss guidance, I would not have achieved this. I am very, very thankful, grateful to my PhD boss, Professor Larmor. I am also very, very thankful to my US boss, Balraman Kalyanaraman, Professor Balraman Kalyanaraman, Chairman, Biophysics Department, Director, Free Radical Research Center, for giving me this wonderful opportunity for teaching me and training me to achieve this. I have carried out all my research works with our collaborative researchers. I thank all the collaborative researchers for making the research achievements. Finally, I thank all my research scholars, former research scholars and present research scholars for their support and for their hard works. They are now in USA. In the following, you will see the advanced EPR, low temperature EPR using liquid helium up to, you can go down up to -4 Kelvin facility, saturation recovery EPR instruments fabricated in this lab, indoor EPR instrument, etc. Thank you all for joining me. This is possible because of the organizers of this meet. The principal, Dr. Jayanti, HOD of Biochemistry and Chemistry, Head of the Department, Government Arts College, Krishnagiri. Because of the time limitation, I could not complete fully. Hope you will join me in future, the part 2, part 3 presentations. Kindly watch the videos on EPR instruments, Niagara Falls, Sears Tower, etc. Thank you.